Hello everyone, myself Michael Ravina, Associate Professor, Department of Computer Science and Engineering. The subject is CS3551 Distributed Computing and the unit is Distributed Mutex and Deadlock. In this video, we are going to discuss about KNAPP'S classification and algorithms for the single resource model. KNAPP'S classification. Distributed deadlock detection algorithm can be divided into 4 classes. First one is a path pushing, then second one is edge chasing, then third one is a diffusion computation, then fourth one is a global state detection. First one is a path pushing algorithm. In path pushing algorithm, distributed deadlocks are detected by maintaining an explicit global WFG. The basic idea is to build a global WFG for each side of the distributed system. In this class of algorithm, at each site, whenever deadlock computation is performed, it sends its local WFG to all the neighboring sites. After the local data structure of each site is updated, this updated WFG is then passed along to the other sites and the procedure is repeated until some site has a sufficiently complete picture of the global state to announce deadlock or to establish that no deadlock are present. Then second one is the edge chasing algorithm. In an edge chasing algorithm, the presence of the cycle in a distributed graph structure is to be verified by propagating special messages called probes along the edges of the graph. These probes messages are different than the request and reply messages. The formation of the cycle can be deleted by the site if it receives the matching probe sent by it previously. Whenever a process that is executing receives a probe message, it discards this message and continues. Then third one is a diffusing computations based algorithm. In this algorithm based distributed deadlock detection algorithm, deadlock detection computation is diffused through the WFG of the system. This algorithm make use of the echo algorithm to detect the deadlock. This computation is superimposed on the underlying distributed computation. If this computation terminates, the initiator declares a deadlock. To detect a deadlock, a process sends out query messages along all the outgoing edges in the WFG. When a blocked process receives first query messages for a particular deadlock detection intimation, then it does not send a reply message until it has received a reply messages for every query it sent. Then fourth one is a global state detection based algorithm. Global state detection based deadlock detection algorithm exploit the following fact. First one is a consistent snapshot of the distributed system can be obtained without freezing the underlying computation, and if the stable property holds in the system before the snapshot collection is initiated, this property will still hold in the snapshot. Therefore, distributed deadlock can be detected by taking a snapshot of the system and examining it for a condition of a deadlock. The next one is a Mitchell and MERRITT'S algorithm for the single resource model. This deadlock detection algorithm assumes a single resource model. This detects a local and global deadlock. Each process has assumed two different labels, namely private and public. Each label is accounted and the process ID guarantees only one process will detect a deadlock. Probes are sent in the opposite direction to the edges of the WFG. When a probe initiated by a process comes back to it, the process declares deadlock. Each node of the WFG has two variables called labels. First one is a private, then second one is a public. In a private label, which is unique to the node at all the times, though it is not constant. Public means it can be read by the other process and which may not be unique. Each process is represented by a U by V, where U and V are the public and private labels respectively. Initially, private and public labels are equal for each process. A global WFG is maintained and it defines the entire state of the system. The algorithm is defined by the 4-state transition diagram shown in the figure. Then the block create an edge in the WFG. 2 messages are needed, one resource request and one is a message back to the blocked process to inform it of the public label of the process it is waiting for. Active denotes that the process has occurred. The resource from the process is it was waiting for. Transmit propagate large labels in the opposite direction of the edges by sending the block message. These are the 4 possible state transitions. First one is the block, then second one is the active, then third one is the transmit, then next one is the detect. Whenever a process receives a probe which is less than its public label, then it simply ignores that probe. Detect means that the probe with the private label after some process has returned to it, indicating a deadlock. The above algorithm can be easily extended to include priorities where whenever a deadlock occurs, the lower priority process gets aborted. The complexity, if we assume that the deadlock persists long enough to the detector, the worst case complexity of this algorithm is S of S minus 1 by 2 transmit steps, where S is the number of processes in the cycle.